All right, here we are in chapter 2, which is going over what they're calling the chemical level of organization. So as we talked about in chapter 1, we're going to look basically at atoms and molecules here in this chapter. Now, I will say there is a ton of information in here, right? In Gen Bio 1111, I might spend a couple weeks going, actually maybe 3 or 4 chapters going over this information. So hopefully for most of us, this is going to be review. If not, you might need to spend a little bit more time in this section making sure you're kind of up on the amount of chemistry that you need to know to really understand how the human body works. Okay, so what we're going to start out with then are atoms, right? And atoms are basically the simplest form of matter that are actually stable. Now they're made up of some subatomic particles, protons, which have a positive charge, neutrons, which have a neutral charge. I'll just put that as a 0, right? So there's our neutron. Now both the proton and the neutron are located in the nucleus, in the center of this atom, and then they're orbited by electrons. And electrons have a negative charge. The reason an electron actually stays on this atom is that it is attracted to that oppositely charged proton, okay? So protons and neutrons are in the nucleus, and they also are the subatomic particles that have mass, or at least enough mass that we count it, right? And so if you put the proton, I should start it this way, sorry. The other way to look at protons is the number of protons that an atom has determines what it is, what element we're talking about, right? So we'll spend a little bit of time looking at the periodic table here, right? But this big number up in the left corner tells you the atomic number, and that is the number of protons, right? So carbon has 6 protons, oxygen has 8 protons. The different number of protons is going to make these elements different, right? And that is what we call the atomic number, and it really is that number of protons. The other number, and I know it's hard for you to see this, but the other number that ends up being important on the periodic table is the atomic, this is probably atomic weight, but atomic mass is fine. Basically what we're looking at there is the sum of the protons and neutrons. Now, a couple hints for you. Typically, what we're going to see is that an atom has the same number of electrons as it does protons. Typically, when we talk about an atom, we think about it being neutrally charged, right? So if you know the number of protons, you basically know the number of electrons. The only exception to that would be if you're dealing with what we call an ion. An ion is going to have a different number of electrons than protons. And we'll come back and talk about that a little bit more, but if you look at something like an example that you'll definitely see in this class is a sodium ion, right? It shows us that there's a charge on this, right? In this case, the positive charge lets us know that there's one more proton than there are electrons. If you look at something with a negative, an ion with a negative charge like chloride here, we know it has one extra electron than the protons, right? But in general, we tend to think of those as matching. Ions are the exception to that, but a very important exception that we'll use a lot in this class. We also typically assume that the number of neutrons is the same as the number of protons. So if you know the atomic number, you can make some assumptions about neutrons. If the number of neutrons differs, do you remember what that was called? An isotope. and you would only remember that from Bio 1111 or a chemistry class, right? This isotope is when there is a different number of neutrons than there are protons. Protons are kind of our baseline, right? Same up here, different number of electrons than protons. If the number of protons changes, you change the element that you're looking at, right? But otherwise, we can have some differences here in ions and isotopes, right? We won't deal a lot with isotopes. You could get in those if you went into like radiology field, but we will definitely talk a lot about ions. Okay, so subatomic particles, protons and neutrons in the nucleus together make up the atomic mass. Electrons are orbiting around them. Now, this periodic table has a lot going on, but the good news is that you do not, well, one, you don't have to memorize the periodic table. That would be ridiculous. Two, the periodic table is a tool, and we can talk a little bit about how to use it. And three, if you look at the human body, you're actually made up of, you have lots of elements in you, but it's not near as crazy as the periodic table. In fact, so this table 2.1 out of your textbook is telling you again the percent of your body weight that's made up of certain elements, and you are primarily oxygen, right? 65% of you is oxygen, almost 10% hydrogen. And really that comes down to how much of you, 50, 75% of you is water. Oxygen just happens to be a much larger atom, right? It weighs more. You, of course, as a living being, as an organic being, you have a lot of carbon in you, right? Nitrogen, calcium, phosphorus, these ones together, I think it's this first 6 or 7, make up like 85% of your body weight. So really, if you think about the elements that you need to know and work with, these ones would be a great start. These next 7 or so elements make up another like 1.5% of you, right? So it drops off significantly as to how much of you is made up of things. That said, we will definitely talk about potassium and sodium and chloride and magnesium, maybe a little bit about sulfur, maybe a little bit about iron, right? Those sorts of things, okay? So you'll start to hear some of these elements like sodium and chlorine over and over again. You also are composed of what they're calling trace elements, right? Now, if you look at iodine here, you are 0.0002% iodine. Everything on this list, like molybdenum and cadmium, chromium, you are less than 0.0002%, right? But some of these actually end up still being really important, right? As far as your body functioning, even though you need them in teeny tiny amounts. Okay, so when we look at why these elements are important, a lot of the times when we're talking about them, it's going to be how they're interacting with each other, whether they're making slightly more complex molecules, right, more than one element kind of hooked together, or the way they're interacting with each other and doing things in the body. Now, the way that atoms interact with each other, right, what determines whether they're reactive, right, excited to interact with other atoms, or if they are inert, not interacting, has to do with their electrons, and specifically the electrons in the outermost shell. So what happens here, right, is our electron is attracted to the proton, right? It's kind of like our moon orbiting around Earth. There's a pull. Gravity from Earth is kind of holding the moon in this orbit. And that's kind of how I think about these electrons working as well, right? So they're actually kind of held at a certain distance from that nucleus, depending on how strong the attraction is. So what they're looking at here, so here is hydrogen, right? This is one of those top 6 elements that makes up a big portion of you. And it is also the simplest, right? This is a great element to look at. It has a single proton, and most of the time, unless you're talking about an isotope of hydrogen, most of the time it doesn't even have a neutron, right? It's a proton, and that charge is balanced out by an electron, and so we see hydrogen, no charge there, because it's neutral, right? It's balanced. Its atomic number, remember atomic number was determined by the protons, so that is 1. Atomic mass was the protons plus the neutrons, 1 plus 0 is 1, right? And that electron is balancing the proton, right? Great element here. Now, when we think about how electrons orbit, they end up following these rules. This is kind of one of those things that you just have to memorize, right? Here is an example of helium showing you that you can have 2 electrons in that first, what they call an orbital, or that first shell, right? From there, we start adding on. If you get more than 2 electrons, you start adding on shells. So the way this works is that innermost orbital, I'll just call it the first orbital, can hold 2 electrons. The second holds 8 electrons, and the third holds 8 electrons as well. All of the elements, there can be more shells, but all of the elements that we'll talk about work in these first 3 shells. So this is what you have to remember. In that innermost shell, if it's full of electrons, there's 2. Now, hydrogen only has 1 electron. And this is where we said that outermost shell is called the valence shell. And that could be the first, second, or third shell, depending on how big this atom is. In the case of hydrogen here, that first shell is also the outermost shell. And because hydrogen only has 1 electron, what we'll see is that it really wants 2. 2 electrons would just would complete this element. It would be happy, it would feel fulfilled in life, right? As helium does. So helium with 2 protons, 2 neutrons, and 2 electrons, right? Those electrons are balancing out the protons. That valence shell is full. Hydrogen is very reactive because it's missing an electron. It's trying to complete itself. Helium is inert. It does not interact with other elements because it's already happy, right? So that's the thing to keep in mind here with these orbitals. That valence shell, the number of electrons there, really determines interactions with other atoms, right? So here we see lithium, right? Lithium, notice the atomic number is 3. There's 3 protons, and then the corresponding 3 electrons. The first 2 fill that first shell, and then we have to add a second shell. How many does the second shell want? 8. How many does the second shell have? 1. It has a lot of work to do if it wants to fill that shell, right? Or it can let go of that electron and come down to only having 2 electrons on that innermost shell, and it could feel fulfilled that way. But if you had 3 protons and got rid of that electron, right, you would then end up with an ion that had 1 more proton than an electron, right, and so it would be positively charged. Okay. Neon also has 2 shells, but notice here the atomic number is 10 protons. The first 2 electrons go in that inner shell, 8 in the next, that equals 10, right? And so having 8 in that valence shell, neon is also an inert gas. It does not react because it has all the electrons that it wants, right? And so those are the kind of things that we're going to be looking at. That's going to be important in how different atoms bond and interact with each other. Okay, before we go on, let me show you one trick before we do this. Okay, check this out. In the periodic table, this is arranged. This is actually super clever, right? This is actually arranged so that you can tell how many electrons are in the outer shell. Anything in this row is going to have one electron in its valence shell. Remember, hydrogen only had one. It was looking for another. Lithium, we saw 3 electrons, so there's only one in the outer shell. That's true of this entire column. This column has 2 in the outermost shell. You skip this whole center section, right, and come over here to this, what they call 3A. This all has 3 in the outer shell, 4, 5, 6, 7, 8, right? And these are inert molecules because they have either 2 in the outer shell, 8 in the outer shell, 8 in the outer shell, and so on, right? So the column that you're in tells you the number of electrons in the valence shell. Okay. The row that you're in tells you how many shells you're dealing with, right? So we saw, that's number 1, we saw that hydrogen and helium each only had that first shell that can hold 2 electrons, where we saw lithium and neon move up to having another shell, right? And that goes on and on. And again, I said you really only had to deal with up to 3 shells, right? And you'll notice there's sodium, there's chlorine, right? We talked about oxygen and nitrogen and carbon, phosphorus, sulfur, right? So the things that we're dealing with are really primarily in these first 3 rows. Okay, sorry, that was a little trick there. If you haven't taken chemistry, that one might be new. Okay, they gave you this really nice 2-4. They were trying to point out how chemists write this in shorthand, which I thought was actually nice, because I think we skip over this a lot of times, right? Like, I take it for granted that you know that H2O is referring to a molecule that has 2 hydrogens and a single oxygen. But they lay it out here for you, right? If you're just talking about 2 separate hydrogen atoms, you would write that 2H. But that is different than an actual hydrogen molecule where those hydrogens have bonded together and then it's H2, right? So that's why we have that little subscript notation. That indicates when we've moved up into complexity into molecules. They also did a nice job here of showing you how we kind of shorthand a written reaction, right? So here they're showing you the reaction of how to make water. Notice this arrow is indicating the actual reaction, right? Here they're showing you what they call the reactants. Sorry, you probably can't read that. Reactants are always on the left-hand side of the arrow. That's what's going into the reaction. And then there we see the water molecule, right? So they're showing you hydrogen, hydrogen, and a single, wow, how do you do oxygen? I guess like that, right? And that's becoming, the actual water molecule, right? And then they're also showing you ions down here, and we'll talk a little bit about how these form. But again, if you lose an electron, so now you have one more proton than a neutron, you would become positively charged. And so in our ions, I guess we're just doing that right here. We have cations and anions, right? Cations are going to have a positive charge, like they're showing here with sodium. And again, that means there's one less electron than there are protons. And anions are going to have a negative charge, like chloride, right? One less electron makes it positive. I think sometimes people get a little confused by that. And one more electron gives us that negative charge. And people tend to be a little bit better with that, right? If you see this kind of annotation, calcium is another example of a cation, but it actually gave up 2 electrons. So it has 2 more protons than electrons, and so we write it as 2+. This will come up as we're working through class. If this comes up later in the semester and you're like, how did that work? Remind me. We can go over it again, because that's really how stuff sticks with you as you start using it and applying it in different situations. Okay, hey, look at this. Now we're really getting into how those ions form, but now you've got your language, cations and anions. And if it helps for some people, that the T looks like the plus sign to help you remember that that's the positively charged. Okay, so here's how that ion actually forms, right? Notice sodium here. Let's look at our periodic table real quick. I say real quick, but let's see where it is. It's always nice when it's just in a classroom. Here's sodium. Sodium's atomic number is 11. Right, that's what they're showing you here. Now, what do we remember about the atomic number? It tells us how many protons. Good. So here we'll switch back to, okay. So if our sodium has 11 protons, we would expect that it has 11 electrons. Let's check. In this first shell we have 2. We go out another shell and there's 2, 4, 6, 8. So we're up to 10 so far. Yep. And there's number 11. So this is actually into that 3rd shell. Okay. Now, how many does it want in the 3rd shell? 8, and we only have 1. So this atom is actually very unstable. Now, if it loses that electron, it's going to shrink back to now only having 10 electrons, but that outer shell being full. And this is exactly what happens. Typically, you see sodium and chloride together because chlorine's atomic number, I believe, is 17. Let's count it, 2. And there's another 8, so 10, 11, 12, 13, 14, 15, 16, 17. Chlorine at 17 should have 17 electrons, and notice it's just missing 1. If it could have 1 more electron, it would be in its happy place. And so what happens is these two hang out together because typically sodium is like, oh yeah, if I move down to 10 electrons, I have a full outer shell. I'm now going to be the cation sodium. And chlorine says, oh, well, this is easy. If I just had 1 more electron, I would be happy. But when we get another electron, we become an anion, right? Now, the interesting thing is that's actually what holds these 2 elements together, is what we call an ionic bond, where a cation and an anion are attracted to each other. They're going to hang out near each other because those opposite charges attract. Right? So people get maybe a little confused. I don't know. When we talk about ionic bonding, right, we actually form these ions. One element steals that electron from another, but notice now that positive and negative charge are actually attracted to each other, and that's what makes this ionic bond. And if you see something like table salt, this is actually like physically holding sodium and chloride together. One other point. I'm not real worked up about this, but if you noticed, when this element is in its kind of neutral form, it's called chlorine, and when it becomes the anion, it becomes chloride. I'm not too worked up about that, but if you wondered why I was changing the name, it's what happens, right? Chlorine, chloride. Okay, that's the big one where we see the name change. Most of them don't, right? Sodium is still sodium. Doesn't seem fair. Okay, so that is ions and ionic bonding, right? They're stepping it through here, right? Sodium giving up the electron to chloride, getting opposite charges, and then actually being bonded through that attraction. Okay, now molecules are going to be formed by covalent bonds. And in covalent bonds, those electrons aren't stolen, the electrons are actually shared. right? So what they're trying to show you in this image, right, is that one of these electrons was with this hydrogen and one was with that hydrogen, right? Here's a shorthand. You can show those two hydrogens bonding, or now that you have a molecule, you could actually write that shorthand of H2, right, or O2, okay? Without getting into crazy amount of detail, look at what happens though, right? Basically, these electrons now orbit both of the nuclei of hydrogen. This hydrogen feels like it has two electrons and is happy, and this hydrogen feels like it has two electrons and is happy, right? So H2 as a molecule now is actually quite stable. Each of those feel fulfilled. Oxygen, same thing. Oxygen, here, this is nice, 2 electrons on the inner shell, 2, 4, 6 in the outer shell. Notice this one's yellow, this one's orange. It's looking for 2 more, it's looking for 2 more, and so basically we're each going to share 2 of those electrons that can now go around both oxygen molecules. In this case, you were sharing 1 pair of electrons, so they draw a single line. In this case, you're sharing 2 pair of electrons, and so that's considered a double bond, a covalent double bond. But what we're really interested in is that oxygen molecule. Everybody feels like they have a full valence shell, and oxygen is also fairly inert. So they did the same to show you how this works in carbon dioxide, another common molecule we'll talk about. Heck, check out nitrogen here. You can actually do a triple bond. But again, all of these are molecules, and you'll see that written in the shorthand. Okay. One of the molecules that we will talk about quite a bit here is the water molecule, right? So oxygen, again, had 6 electrons in its outer shell. It wants 8, so it's looking for 2 more, right? And so what ends up happening is 2 hydrogens with their single electrons get attracted. We share a pair of electrons here. We share a pair of electrons there, right? And again, in that molecular form, there are 2 hydrogens and an oxygen bound together. Now, this is a covalent bond because those electrons are shared, but one of the things they're trying to show you here is water is a really unique molecule, and what happens is the electrons get shared unequally, right? There are 8 protons in the nucleus of oxygen. There is only 1 in hydrogen. So if you think about who has more pull for that electron in its orbital, picture this little electron here going around and around and going up there every once in a while, but really being pulled towards that much larger oxygen nucleus. What that leads to is a partial negative charge on this end of the molecule and a partial positive charge on that end of the molecule. And here's your actual notation. It's this weird little symbol showing partial negative, partial positive. For me, as long as you know that this end is more negative and that end is more positive, I'm not super concerned with the technical chemistry notation. But the fact that this is a polar molecule, and they call it polar because now we have poles. The ends are different, right? There's like a north pole and a south pole. It's like a battery. There's a positive end and a negative end. That is different, right, than oxygen, where these things are equally shared. There are no poles, right? This electron spends just as much time around each because it's equal pulling, okay? Polar molecules, right, are going to behave very differently, and that is part of what makes water so important, okay? We will talk more about water here momentarily. I tossed this in. All this talk about electrons filling valence shells, I did want to point out, you've probably heard of free radicals. A free radical is going to basically be an atom or a molecule where it doesn't have a full valence shell of electrons. It's still trying to grab an electron from somewhere to kind of balance itself out. And what we see in free radicals is they're very reactive. They're trying to find that electron. They'll typically steal it. This is showing you a cell membrane. They'll try to steal electrons there, maybe even from DNA. And so they can be very damaging, right? They're part of the aging process, whether they're damaging DNA or whether they're damaging cell membranes, right? That's leading to things like wrinkles. And so what's the antidote to a free radical? Have you heard of... If you've been to Natural Grocer, you've seen the term antioxidant a lot. Antioxidants are essentially the antidote to free radicals. So things like vitamin E, vitamin C, selenium, these different molecules are willing to donate those electrons and basically stabilize that free radical, make it happy, less reactive, so it can't damage other things. Okay, just wanted to throw that out there. Okay, let's talk a little bit more here about water, and then we'll take a break. So that water molecule that we're talking about having a partial positive and a partial negative charge sets up a situation where we get a weak bond forming between adjacent water molecules. If you recall, and that's why they're doing it with a dotted line, because it's a weaker bond. But this is what we call a hydrogen bond. So the partial negative of one hydrogen on the water is attracted to the partial negative of the oxygen on another. This is also a very important factor as we look at water. This is what provides surface tension, right? So insects that can run across the surface of the water and that sort of thing. It is because the hydrogen bonds are holding adjacent water molecules together. This is what gives water what we call like a high thermal mass, that it can absorb a lot of heat before it goes from being a water to a gas, right? Or before it changes temperature. Because in order, right, to go from being a liquid to being a gas where those molecules can spread way out, you actually have to break all these hydrogen bonds. And so it actually takes a lot more energy to turn water into a gas than a lot of other molecules. I'll come back to the other slide. This is the one I was looking for, right? And so when you think about water, right, your body is like 75% water. This is a very important molecule. Because it's polar, it can act as a solvent. It can help break things down. So if you think about, we were talking about sodium chloride being held together by ionic bonds. When you put that in water, you actually rip the sodium and the chloride apart. Now think about why that happens, right? Sodium, with its positive charge, basically gets surrounded by water molecules with all their oxygens facing in, right? The negative part of that water molecule. Notice what happens to chloride here, this big green blob. All the hydrogens, all the positive ends of water are attracted. And so basically when you drop table salt into water, it gets ripped apart. Sodium and chloride are separated and basically surrounded by water molecules, right? And so we call that a solvent. So there's another kind of reaction for you. A solute, like table salt, and a solvent, like water, that could help break it down. Give you a solution, right, where you have sodium and chloride ions separated in here. So that sodium and chloride are now separate in that water, right? So we've pulled sodium and chloride apart. We still have whole water molecules separating them. So solute is what's dissolved. Solvent is who does the dissolving, and solution is the end product there. Okay. Reactivity, we'll see a lot of our reactions in the body taking place in aqueous environments. We will see that if you want to break something like sugar, like a complex sugar down, you are going to use water in a process called hydrolysis. Literally, lysis is splitting. You're using water to split things apart. We'll see that when you try to put molecules together into something more complex, we do what's called a dehydration, which is exactly what it sounds like. You pull a hydrogen off of one molecule, an OH off the other, you make a water molecule, you pull that out, and you stick the other two things together, right? So a lot of our reactions are going to involve water molecules. We already talked a little bit about that high heat capacity, how the hydrogen bonding in water makes it hard to break it apart. And then of course in the body, we'll see water being used for a lot of lubrication, whether that's tears, whether that's the fluids in joint spaces, or even say the pericardium, the sac surrounding your heart, right? We need that lubrication. So water ends up being super important. We will talk about it a ton. One more note on water, this idea of solvency. Do keep in mind, a lot of times people say water is the universal solvent, but that's not really true, right? So we just were looking at how sodium chloride can break down in water. But basically what we would say about that is that molecule of sodium chloride is actually hydrophilic, right? It loves water, it's attracted. Same would be true of things like glucose. You can dissolve sugars, things like that in water. But what you can't dissolve in water are hydrophobic substances, right? Things that fear water, and primarily this is going to be things like fats and oils. And that will definitely come up in how humans as a living organism function. Okay, so it's great for breaking down, dissolving a lot of things, but not everything. Okay, pH then is another topic that's very much related to water and is super important to understand. So pH, I think of it as the power of hydrogen, right? And so when we're looking at hydrogen, they're talking about the actual hydrogen ion. Now, hydrogen, if you recall, hydrogen was atomic number 1, so it had 1 proton, right? And that was matched with 1 electron. When we see hydrogen in its ionic form, how would you get the positive charge? You have to have 1 more proton than you do electrons, which mean we've gotten rid of the electron. Hydrogen ion is essentially a single proton all by its lonely self. Okay. When we think about the power of hydrogen, pH is really the negative log of the concentration of hydrogen ions, right? So the brackets mean concentration of, and then we'll talk about this negative log. Now, the thing that's important, right, the applied part of this, is that the number of hydrogen ions that are in your body is really important. If it gets out of whack too far, it'll kill you. Do you know what the pH of blood is? So typically we say the pH of blood is 7.4. 7 is neutral, right? And so a 7.4 would make blood slightly alkaline or basic, right? This end is basic, or the other term is alkaline, right? Anything above 7, below 7 is acidic, okay? So when we say the pH of blood is 7.4, we really, here's a good example of homeostasis. The pH of blood needs to stay between 7.35 and 7.45. How's that for like really tight margins? In fact, if you drop as low as 6.9, just below neutral, you'll go into a coma and potentially die. And really, I think it's around 8 on the other end that the same thing happens, right? So this number of hydrogens is really important. Okay, so the pH scale itself is talking about the concentration of hydrogen ions. So this is what happens. Water can break down into hydrogen and what's called hydroxide or hydroxyl. Okay? And all the time in a glass of water, there are water molecules that are breaking apart, coming back together. This is what we call a reversible reaction. So we actually draw an arrow both ways. Some are falling apart, some are coming back together. Now in a neutral, just a pure glass of water, what you'll find is the concentration of these hydrogen ions is 0.000007, 1, right? And in scientific notation, we would write that as 1 times 10 to the negative 7th, right? 1, 2, 3, 4, 5, 6, 7 decimal places, right? To the left, 1 times 10 to the negative 7th. That is why neutral is 7 instead of like it being 0 in a negative scale and a positive scale. It's the actual amount of hydrogen ions, a very small number that you would find in a pure glass of water. Now, that's the concentration of hydrogen ions. All this logarithmic scale says is that it's base 10. So a pH of 6 has 10 times as many hydrogen ions, as a pH of 7, right? A pH of 5 would have 10 times more than a pH of 6. It's like the Richter scale, right? So it's exponential. But that also means that a pH of 5 is 100 times more acidic than a pH of 7, right? 10 times 10, okay? That's the log portion. Ooh, and the negative is that it's an inverse, right? So more hydrogen gets you lower numbers. Does that make sense? Right? So acidic has lots of hydrogen. Basic has very little hydrogen. It has a lot of that hydroxyl ion. Okay, the pH scale, pH is definitely going to come up in multiple different chapters, probably mostly in A&P 2, but it really is because the body maintains such tight control. And it does so because those hydrogen ions are dangerous. They will break down cell membranes, they'll destroy proteins, all those sorts of things. So don't be scared of the pH scale, just spend a little bit of time with it. If that's still confusing you, we can absolutely go over pH some more in class. Okay, the other thing I skipped, there was a slide I skipped, let's make sure we hit enzymes. Okay, so as we're looking at reactions throughout the body, let's do this. Okay. Metabolism is all the chemical reactions in your body, and we typically split that into 2 different types of reactions. Do we remember this maybe from chapter 1? Catabolic reactions are breaking things down, as in you're going from a complex molecule to a simpler molecule. So for me, I think of something, hey, it can be as easy as this. You take a disaccharide like sucrose. Sucrose is made up of glucose and fructose. They're bonded together, right? You can break that down into those individual monosaccharides, right? Those individual sugars. That would be a catabolic reaction, right? Catabolic reactions release energy. Anabolic reactions are going to take simple molecules, put them together, and build that more complex, in this case, the disaccharide, and that actually takes energy to make that happen. Okay? So throughout the body, you have all these different catabolic, anabolic reactions taking place. Maybe you think about what you've consumed in your food as providing both the energy and the building blocks to then go into these anabolic reactions so you can build protein, so that you can store energy in the form of fats, all of that, right? So we'll see lots of different reactions. And a lot of the times we just talk about it with one arrow, right? Showing you one reaction. But in reality, you have these crazy metabolic pathways. In fact, in the lab, there's a poster that just has so many arrows showing all of these complex metabolic reactions, right? Where it's not just like A plus B gives you C, it's then like, well, okay, and then there's this reaction, and this reaction, right? And on and on. Sorry, I just made that really confusing, right? But there's a series of reactions in what we would call a metabolic pathway. Okay, which either of these really brings us to enzymes. So basically, in order to go from a reactant to a product, right, from the left-hand side of the arrow to the right-hand side of the arrow, we have this reaction. And a lot of the reactions that happen in the body need some help, right? And so basically for this reaction to take place on its own without any help, it would need like this big input of energy to kind of kick it off, get it started. And what enzymes do is they do what we call lowering the activation energy. They basically make it much easier for this reaction to proceed, right? And I should have a picture of this somewhere. I'm about to flip through a bunch of slides. Hold that thought. I don't have a picture of my enzyme. It's a protein, so enzymes are always made out of proteins. Here we go. Wow. Okay, so enzymes are always made out of proteins. And notice what happens here. There's a location on this protein, we call it the active site. It's going to fit, in this case, two separate substrates, right? And it puts them in this position where they're very closely aligned, and it's much easier for them then to become this product, right? So substrates, here's the actual reaction, and there's our product, right? And this can work the other way as well. So you could have an enzyme that takes a complex molecule, and the enzyme can change shape and kind of pop it apart into two individual products, right? So enzymes, by bringing these substrates into the correct orientation, actually make this reaction much easier to take place, hence that idea of lower activation energy.